Today, I will be presenting this talk on short and long-term memory as an essential ingredient for long horizon manipulation. And this is basically, or like it mostly covers one of my papers during my time at Physical Intelligence that we call MEM, Multi-Scale Embodied Memory for Vision Language Action Models. So here I want to also show some of the tasks. These are like some super dexterous tasks that I think are super cool, but they are kind of short horizon. So we have spreading or like making a peanut butter sandwich, like folding some socks and inside out t-shirts, and then unlocking a lock. I think this is very cool because they are very dexterous and all, but it is not the like it just feels like kind of a subtask of that we would want to achieve, right? For example, you might want to assemble something, so you need to unlock the toolbox and then do something else, right? So this just feels like still fairly short horizon. So let's think a little bit about what would the type of long horizon task that I would be super excited to see robots do. One would be type of like doing for the robot to do some type of manufacturing to be able to assemble and build some new gadget. It would also be great if it could get into like a super messy bedroom and could now just clean it up completely, which would involve folding t-shirts, but also making the bed, wiping the floor. And then one of my favorites is making like the robot getting into a new kitchen and being able to cook a full meal for you, which means preparing the ingredients, cooking the meal, and then cleaning up the kitchen. So, like, if we think about this, what are we missing in order to be able to solve these long horizon tasks? So some of the things are like, well, the robot should be able to keep track of task progress, like remember at which stage of, for example, preparing the meal it is. It should be able to keep track of time too, if it's cooking something. Something super important is that it should also have high reliability of dexterity. And this is especially important when we do long horizon tasks, because, for example, if we have a subtask success rate that is something like 90%, now if you accumulate a lot of them, like 7, 10, or 10 of them, now the full task success rate will be very low. So we somehow need to like also get high reliability of the dexterity of the models. We also need the capacity of adapting in context. Maybe you see a new kitchen that you hadn't seen before and you need to adapt to your mistakes there. Or if you make some mistakes, it should be able to react and then correct them. And it should also remember what has been tried before and what has been done, and many other things. But at least I feel that all of these tasks or like all of these ingredients that I feel are important to solve these long horizon tasks could be obtained if we added memory to our policies. So my claim is that we need memory in order to be able to solve long horizon tasks. And here are some examples that we have where like robot tasks that require memory. So here on the top left of the screen, you can see this task of preparing the ingredients to cook a recipe. And the robot will have to do a bunch of different sequence of tasks and it will have to remember what has been done before. So here it put the pot on the sink. Now it will go to the fridge, get some ingredients. It needs to remember which ingredients it has taken out of the fridge and all. And so this the type of like task progress memory that the policy needs to keep. But then we also have some other tasks, such as now unpacking the items in a grocery bag. This may be a priority. We might not think that it needs memory, but it actually has the none of the cameras can see the inside of the bag at all times. So the policy needs to remember whether there's still some items to remove, or if it's done and it should just discard the bag. And this is basically it needs memory because of occlusion. However, if we look at the policies today, most of them don't have memory. An example is PIO5, where if you can see the observations it takes as input is just like the single frame of the current time step. And similarly for CRUD and other of the state-of-the-art VLAs. But now what we see is like if we do some of the tasks, so here we have one task where we are washing the dishes, and if we don't add memory, so this is a policy that we train without memory, it will just keep washing the dish over and over and forever, because it actually does not know that it has been already like it has cleaned it already, so it will just continue doing it. And then on the right, you can see one where the policy is cooking a grilled cheese. and it just puts it inside, and then it needs to wait for a few seconds in order for the cheese to be able for the grilled cheese to be able to be done. But it just waits forever, and the grilled cheese becomes completely burnt. So, okay, why don't robot policies use memory today? Here, I want to do a little bit. I want to show something that we try to study in this other work with some collaborators at Stanford, which is called Learning Long Context Efficient Policies with Past Token Prediction. And here, well, besides, yeah, memory is hard. And here we observed that there were two main problems. One, that I would say effectiveness. And this basically means that policies perform worse because of distribution shifts and lack of data when you add memory. And then efficiency, which basically means that with longer context, policies become more resource intensive. And then they take much longer to train. You need many more resources in order to be able to train them. But also, it is much harder to do inference, and then you get much lower inference rates. So these seem like two big problems with adding memory. So our solution is compression. We will basically decompose memory into two different types. This is an overview of the system that we propose. So basically, we will add a short context into the VLA, which will like the low level VLA, and basically this short context will involve of dense frames from the last few seconds that are needed for dexterous manipulation. And then we will also add some long context memory. This will basically be a compressed language representation of the last minutes now instead of seconds for general reasoning. And this will go into the VLM that steers the VLA. Let's start looking into how do we add this short-term dense visual memory. So we propose a new architecture. This is the video encoder that we use in MEM. And this basically is an efficient video encoder for compressing this short horizon frame-based history. So our architecture expands the standard VITs for encoding videos, and it just starts from a pre-trained VIT, but we will interleave together with the spatial attention some extra temporal attention in a causal manner, so that basically the current frames attend to all of the previous frames. Then we will, at the later stages, we will discard all of the history tokens and we will keep only the current tokens. These current tokens, though, still have all of the information of the past because of these temporal attention layers. And the benefit of this is that basically now we're dropping all of like we have a lot of compression since we still keep as if it was for a single frame, but it actually attended to the whole history. And after these image embeddings are passed into the transformer. So as you can see, all of this compression happens very early on in the VLA. So why is this architecture good? First, it has an easy VIT initialization since only the temporal attention is new. It has, as I mentioned, all of the history tokens are dropped. So we have very high compression of the image sequence so that no matter the sequence length, you still, or like the VLA transformer backbone still only receives as if it got like one set of tokens. And with this, we obtain very fast inference. So let's see what are like this new category of tasks that adding short-term memory help us solve. So here we have one example that is like one of our favorites when I was there at Pi, and is this very dexterous task of cooking a grilled cheese. So here the robot will pick up like each one of the breads, we'll put the cheese, and we'll let it cook. It will have to like wait for a little bit. This is the part that needs memory. It will have to flip the grilled cheese and then flip it again, and it will be done. While it is cooking the grilled cheese, we can also see the other set of memory benchmarks that we set up. Some were specifically done for stress testing memory, such as like swapping mugs or finding the item in a drawer. But some of them were some that maybe people don't necessarily think that they need memory, such as unpacking grocery items from a bag. And needs memory because of occlusion. But also another example is cleaning a window. Here it needs to remember how much it has cleaned. Otherwise, it just keeps going on forever. And now as you saw, the grilled cheese was done. So, okay, so I showed these videos that are super cool, but I also wanted to mention some very important details in order to be able to solve these tasks. And this is one of them, which is that basically, as I mentioned before, the efficiency of the policy is very important. When I was there at Pi, we had these basically this line that we said the latency of the policies cannot pass the 300 milliseconds. If it becomes lower than that, then the policy performance will drop dramatically. So we had to really try to make sure that the inference latency is very low. And here we observe that with our mem encoder, even with 16 frames, we're still under these like threshold that we set. There's still, of course, a lot to be done, but this is much better than just concatenating images into the transformer because this just makes the latency or the inference time increase very significantly. Okay, now let's look into the long-term textual memory. So we will keep this type of system that was proposed also in PyO 5 and other works that basically consists on having a low-level VLA that produces the actions, and then we have a high-level policy that predicts what is the next subtask that should be done. And we decide that this long-term memory should go into the high-level policy because basically this minute-long memory traces should be used just to steer the policies to whatever it should do. So one naive way of adding textual memory would be to just pass each one of the language subtasks as a memory. So we could just keep appending it into a queue, and this could be the memory. This is already much more compressed than having images, since text uses many less tokens. But it is actually not physically accurate. If you think about it, for example, here it says pick up the potato because this was a subtask that was predicted by the high level, but it actually doesn't mean that it did pick up the potatoes. Maybe the potatoes fell on the floor or something. So they are not physically accurate. And it is also very prone to distribution shift. For example, in this case, it might say pick up the masher, but maybe the policy is a little bit slower, or maybe it does a mistake, so it keeps saying pick up the masher many times. Um, Now, maybe in your demos, you did not see the policy or like, the operators failing as much. So here you will get this distribution shift potentially. So, okay, what do we propose? We instead propose for the high level policy to actually predict its updated memory and feed it back into this high level policy as like basically recurrently. Um, and the benefit of this is that we still have text, which is much more compressed than images, but it is also more physically accurate because the policy will update the memory based on the physical events that occurred. So, for example, if the potatoes fell on the floor, it can update the memory saying that the potatoes fell. It is also less prone to distribution shifts since this policy will not update the memory when nothing happens, right? If you see that, oh, it is trying to pick up the masher and it keeps retrying, then the policy will just wait for it to be completely done before updating the memory. So it should also be less prone to distribution shifts. So now let's look at some cool tasks that we can solve with our MEM system. And this is again the example that I showed before. So we need to prepare the items for cooking a recipe. And in this case, we're doing mashed potatoes. Something very nice is that here we're showing what the memory looks like, and how the policy keeps updating whenever something happens. So now it says like, oh, I opened the fridge door, etc. And it will just keep like as you will see, it needs to retrieve a bunch of ingredients and do a lot of things. So here I will go through it a little bit quickly just for the sake of time, but we have more videos on the website. I think it's quite exciting to see how the policies can actually keep track of this memory quite successfully. Okay, and we also see that our MEM policies generate to many different recipes in many on-scene kitchens. So here you have mashed potatoes on some kitchens, then fried rice on others, crepes, and pizza. So again, we did see the recipes, but the kitchens in this case were completely unseen. Something I think is quite exciting is or quite interesting is that when we start doing longer and longer tasks, then this will start needing some very detailed and long text descriptions of what is it that we want the policy to do exactly. And here are some examples of the prompts that we were passing the policy in order to be able to for the previous task of preparing the ingredients for the recipe. So as you see, like we actually give a lot of details of where are each one of the ingredients in the kitchen, or what are the steps, what does it mean to make mashed potatoes, what are all of the different steps that need to be done. We also see that we also train our MEM policies to solve other tasks, such as in this case, cleaning the kitchen. Um, and here again, it consists of doing a bunch of different things. I'm also gonna skip through it quite quickly. It's like what happens when we do a very long horizon task. So it like wipes the counter, then it will dry it. It will put away the items. And as you see, the memory keeps updating with everything that happens, which is quite nice. Put away the plates, then it will wash the plates, and it will be done. So we compare these our MEM policies to other relevant baselines. One would be the completely no memory, which doesn't work too well because these tasks do require memory. And then we also try to test against only video memory and only text memory. And here what we observe is that both perform quite poorly. And when we look at what happens exactly, is that when we only train with video memory, the policies they kind of lose track of task progress and might be switching between two different tasks. Or for example, it already retrieved the mashed potatoes from the fridge and it might still want to go back and pick them again. However, when we only have text memory, then we will see these problems that some of the subtasks cannot be completed, such as washing the plates and all this. It will just keep washing forever. So it is quite important to have both the long horizon text memory and the video memory denser. We also tested against these naive text plus video memories, like what would happen if we instead just pass all of the subtasks as memory. And as we mentioned, it's probably because of distribution shifts, where now the performance here is also quite low. Okay, one of the very cool benefits that I think are super exciting of adding memory is that this should enable in context adaptation. So here I wanted to show a couple policies that we trained without any memory and is a little bit out of distribution. So the table height is a bit lower. And as you can see, the policy is trying to pick up the chopstick and will just go on and on forever since it's not able to react to whatever happened before. And then on the right, you can see for another one where it's like opening the fridge. In this case, this fridge is quite interesting because it's fully symmetric. So you don't really know visually where the hinge is. And in this case, the policy just keeps trying to open the fridge from the right and gets completely stuck. Um, So the very cool thing here is that now when we equip our policies with memory, these are able to adapt in context. And in the case of the chopstick, for example, it will fail a couple of times, but then it will be able to adapt to the height and go lower and place the chopstick correctly. Or for example, when doing this fridge opening task, it will try on one side of the fridge, and when it sees it wasn't able to open it, it will go to the other side to try from there. This only emerges when you add memory. I think it's like one of the very cool benefits of adding memory. And of course, it needs to be explored further, but it is very exciting to see. Um, then this is like a quite interesting plot. Basically, when we train policies with and without memory, it's also always very important. And like we're always a little bit hesitant. It's like, well, but how does it do on non-memory tasks, right? Do we get any drop in performance? Is there any downside into adding memory to the policies? And in this case, we observed that on average, the policies that have no memory and have memory on these like non-memory tasks, they perform as well. So yeah, it is very exciting to see these results. And because of this, now memory can be one of the main features of robot policies. So in the subsequent policies that or like models that were released by Physical Intelligence, as you can see, they have some observation memory and also some task memory, like text memory there too. Um, However, I still want to say that there is definitely still a lot of research to be done to be able to increase the sequence length, find the right memory compression. Is text the right memory compression or not? Or is there some latent that we could learn instead? Also improve how we get in context adaptation and many more research lines here on long horizon tasks, but also on memory related policies. And I wanted to finish by thanking my collaborators. This was a super big effort there at Physical Intelligence, and I had a lot of people who did great work, especially Carl, who was the co-lead here on in this paper. But Homer, Sergey, Chelsea, and Danny too for all their help. And having said this, I'll be happy to take any questions that you might have.
Yes, thanks, Marco. Any questions from the audience?
Awesome.
Yeah. Any questions on the manipulation task? Oh, yes. Thanks.
Yeah, I have a question regarding the data annotation. So does the requirement of producing a text summary for each stage of the task during the training and the inference brings extra efforts or extra burdens in the data annotation pipeline since we have to annotate the data with the proper stage level annotations for the text summary. Yeah.
Yeah, that's a great point. So in this case, we had two different types of annotations for the memory. One is that given all of the subtasks, we could ask for LLMs to make a memory summarization. But we did get an extra burden cost in asking annotators to specifically label the memory for multiple demonstrations. So yeah, it is you get an extra cost there. Yeah.
Thanks for your great sharing. Uh, so for the short-term visual memory, in the paper you mentioned that you train a spatial temporal attention. So I'm curious about for the retraining, how many data you use?
So, oh, I think I removed this result, but on the paper we also show that um, basically, given that the VIT is pre-trained, you could just do the memory at post-training. But we actually get much better performance if we do the full pre-training that Physical Intelligence does. So, like with all of their data. And then like you get an extra benefit. It still works if you like if some of the memory test still works, but they work much better if you do it at full larger scale. Yeah, with like the all the memory, sorry, all of the data they have there. I cannot give like specific details of like how much data they have, but yeah, this at pre-training it even works better.
All right. Yes, please. We have a back.
Hi, thank you very much for the presentation. Speaking completely about the long-term memory, how directly applicable do you think it could be used for navigation tasks? Do you identify a specific challenge with this, or would it be directly transferable?
Yeah, I'm curious about it too. I'm not sure. I feel like for maybe specifically for navigations, we do have these basically very compressed representation that would be a floor plan, for example, right? And things like these, where if you have to keep track of everything through text, it might not be the best thing. I feel like you could keep track of everything through text. But maybe the best is to have like, some it could potentially be interesting to see is like what if your memory was like building a floor plan, but also having text for some other parts of the task, and then like maybe even some visual memory. So I think it could be transferable, but I'm not necessarily convinced yet that it is the best for navigation.